Section 4, equations of lines. If we have a function and the defining expression is a linear polynomial, so if it has x to the first power, that's called a linear function because your defining expression is linear. So the form is going to be f of x equals ax plus b. That's the general way you write a linear expression. Because it's a linear expression, when you draw a line, when you draw the graph of it, the graph of this is going to be a straight line. Just like when you work with y equals mx plus b. That's all you're doing here. The f is the y value, and then you have an mx plus b type of form on the right side. So you have a straight line. Different way you can write that is the standard form, which is a constant times x plus a constant times y equals a constant, ax plus by equals c. This is the mx plus b form. This is the standard form. Remember that the slope of the straight line is how steep it is. It's the rise over the run, or delta y over delta x. This is the defining formula. Make sure you know that you remember that, know how to calculate a slope. If you're given a graph, you should be able to pick points and calculate a slope from the graph. If you're given a slope, you should be able to, well, if you're given a slope and a point, you should be able to draw a graph. This is the defining function. Remember, it's always the x's on the bottom and the y's on the top. Vertical divided by horizontal. If you have a horizontal line, the slope is 0. If you have a vertical line, the slope is undefined. There is no slope for a vertical line because you have to divide by 0, and that's undefined. When you're working with graphs, you can do something called the average rate of change, and that has to do with the slope of a straight line. So we just talked about what the slope of a straight line is. That can be used on any type of graph to get an average rate of change. So if you have a graph wiggling all over, you can say what the average rate of change is between 2 points by drawing a straight line and calculating the slope of that line. That's a very rough measure of the change in a function, and is sometimes useful when you're working with data to be able to get that. It's not accurate, it's not precise, but it gives a rough estimate of how the values change. We're going to look at it first when we're talking about straight lines, where it is completely accurate, but then we'll apply it to a set of data points that are not straight lines. So if you have a linear function, and it's defined over this interval, so this is your input, this is your domain. The average rate of change on that is defined as the value at this end, the value of f at this end minus the value of f at this end, divided by how far it is between those 2 points. If you go into calculus, you'll see that as the definition of slope, and then you'll work more with that. But f of b minus f of a over b minus a. Here's an example where we're going to estimate that average rate of change from some data. So this is the setup, DVD players. And we know, well, you can pretty well be assured that the change going 2001, 2002, etc., up to 2006 would not have been a nice, accurate straight line. It's going to kind of bounce up and down depending on the economy. But we can get an average rate for that by picking those two endpoints. You look at those as if they are ordered pairs. In 2001, you had 12.7. That's a relationship between those two numbers, therefore it's an ordered pair. Similarly, in 2006, you have 19.8. That's another ordered pair. The definition of slope depends on using the values from two ordered pairs, an x and a y value from each pair. Using these as your two ordered pairs, you can calculate the average rate of change between 2001 and 2006. You do the y values, the 2006 number, and remember slope, it doesn't matter which order you put your points in, as long as these first two values come from the same point and the last two values come from the same point. So I can pick 19.8 in 2006 here, 12.7 in 2001 there, or vice versa. And it's still going to give me the same answer. As long as you are consistent in these numbers coming from the same point. Plug those numbers in from your two ordered pairs, and you get 1.42. So the average rate of change between 2001 and 2006 was 1.42 million sales per year. That would then be a rough estimate of how things changed. Right. So it started at 12.7 million. Roughly in 2002, it would have been 14.12 million. And in 2003, would have been 1.42 more. Now, I'm sure it didn't actually give 1.42 each year. It, maybe it was flat and jumped up and then kind of, didn't go up as much. So it would have been a wiggly line going up. But average, it would have been this. And that is, to a first approximation, something useful for considering behavior of the sales. It was going up, it wasn't going down. That's, something useful to know. And it wasn't going up a very tiny amount. It was going up a fairly significant portion of the sales. 1.42 out of 12.7, that's a fairly significant increase. Those sorts of things that you can, do some rough cuts at, even without precise information. And that's the utility in something like the average rate of change. So remember, average rate of change means 2 points and calculate the slope. The slope of the straight line is the average rate of change. But it will have units, just like this. The units on this are million sales per year. So average rate of change is not just 1.42, it's 1.42 million sales per year. If you have a graph of a set of data, you can calculate an average rate of change between any 2 points on the graph by using this same idea. Select the points, determine what the values of the ordered pairs are, and calculate the slope. For instance, here's a graph. When you're doing this, you need to read what the axes mean. This horizontal axis is year after something. So how many years after something? Started at 0 years after and goes up 1 year at a time. This one is value of a machine in thousands of dollars. So this looks like a depreciation graph. Company buys a machine. For tax purposes, they say its value goes down so much each year until at some point it's worthless because they wouldn't be able to sell it for anything. Or at least that's what the tax laws allow them to do. And so this is what the graph would look like. So if you're looking at a graph and it says find and interpret the average rate of change, since that really is a straight line, normally it would not be a straight line, but for depreciation you normally do that. You can pick any 2 points you want to on this graph for calculating your average rate of change, and it's going to give you the same number because it's a straight line. Slope's the same everywhere. So pick 2 numbers that are easy to work with and calculate a slope. What would the slope of this line be? Negative what? It's negative, yeah, it's going down. So negative what, though? How'd you get negative 4? Okay, that's 4 units this way, but why'd you get 4 for slope? Yeah, each one of these is only 1 unit, isn't it? But pay attention to that because it could be something more than 1. So you do have to watch what the units are between your points. But yeah, I picked that point and that point, 20 and 4, and so this is 0 and 4, so it's minus 4. But minus 4 what? That is the slope of the line numerically, but what does that minus 4 mean? Average rate of change is minus $4,000 per year. So when you're doing this, you pay attention to the units along this axis, the units along this axis, the spacing here, the spacing there. Otherwise, you could wind up getting incorrect increments and incorrect values for your answer. Average rate of change. Pick 2 points, calculate the slope between them. You don't even have to draw the line if you have the 2 points. Normally you might want to do that just to keep straight what you're doing. But it's a very simple process. So if you encounter a problem where it asks for the average rate of change, that's all you have to do. And you might see one of those.